All right, welcome everyone to the Humanist Society of Santa Barbara's March 2025 meeting. I want to let you know that HSSB is a 501c nonprofit educational organization. We're 100% volunteer run, founded in the mid-90s, and we always welcome new members interested in finding out about humanism, anyone interested in contributing their talents to our organization. We welcome donations. We can take donations via PayPal, or this month we've also added Zelle as a way that you can donate or contribute money to our organization. So today our speaker is Dr. Roger Freedman, talking about from the solar system to the most distant galaxies, 2.5 years of discoveries with the James Webb Space Telescope. And you may wonder, what does this have to do with humanism? Well, I took a look at the affirmations of humanism written by Paul Kurtz, and 3 of them were particularly applicable. As humanists, we're committed to the application of reason and science to the understanding of the universe and to the solving of human problems. We believe that scientific discovery and technology can contribute to the betterment of human life. And we are citizens of the universe, and we're excited by the discoveries still to be made in the cosmos. And our speaker today, Roger Freedman, is an emeritus associate teaching professor in the Department of Physics at UCSB. He's the co-author of several physics and astronomy textbooks, which are used across the US and around the world. In addition to his ongoing work on conventional textbooks, he's co-creating a series of comic book stories designed to help physics students improve their problem-solving skills. And I think it's from these comic book stories that we received this particular publicity photo of Dr. Freedman. So with that, Roger, I'll turn it over to you.
Well, thank you all for joining me this afternoon. As advertised, I want to talk about what's been going on for the last 2.5 years with JWST. So again, I'll be taking you from the solar system to the most distant galaxies. In fact, we're going to do it in the reverse order, just to keep everyone on their toes this Saturday afternoon. I'll begin by saying that JWST, although we think of it as something that was launched by NASA, it really is an international collaboration between NASA. It's actually run through the Space Telescope Science Institute, which is in Baltimore. It's also a big collaboration with ESA, the European Space Agency, and also the Agence Spatiale Canadienne, the Canadian Space Agency. So it really is a multinational operation that's being used by astronomers really from around the planet. What JWST is, it's an infrared telescope. I think most people know what infrared is, but always good to do a reminder. If we look at the spectrum of light, the kind of light to which our eye is sensitive is a fairly narrow portion of the electromagnetic spectrum. One good way to measure the properties of light is in terms of its wavelength. Think of a wave oscillating up and down, and it's really the distance from one wave crest to another. We use these units of micrometers. If you're old school, you'll call that, like I am, you'll still call those microns, which is a millionth of a meter or a thousandth of a millimeter. There are a few third world countries that still use units like feet and inches and so on, but I can't think of any of those countries right now, so we're going to do everything in meters. But if you've forgotten a meters, basically, it's a hair more than a yard. So the human eye is sensitive to wavelengths from 0.4 microns to 0.8. 0.4 is over at the violet end of the spectrum, 0.8 over at the red end. That's a kind of a factor of 2. Interesting, in sound, a factor of 2 in the wavelength of sound corresponds to 1 octave. So imagine how restricted your hearing would be if you could only hear 1 octave of sound. And anything below or above that, your ears couldn't detect it all. That'd be kind of limiting, but that's in fact the way our eyes work. But there's much more beyond that. There are wavelengths much shorter than that, which is the ultraviolet, and wavelengths that are longer, which is infrared. And where JWST comes into play is actually in the infrared. It can see a little bit into the visible, into sort of the red and orange part of the spectrum, down to about 0.6 micron, but it sees all the way out to 28 microns. So coming back to the musical analogy, the visible spectrum is about 1 octave, and JWST, that's about 6 octaves. So it really sees a much broader range of wavelengths and can see things that the human eye never could, and that ordinary optical telescopes can't see. And we'll see going on why being able to see in the infrared is so very important. We normally don't notice infrared because our eyes are not sensitive to it, but in fact, we use it all the time. The picture on the right shows a space heater. Okay, if I'm close enough to it, I feel some heat from it. Well, we see visible light from the space heater, but most of the energy that could come out of that is actually infrared radiation coming from the space heater. In fact, look at the design on this one. It has a reflector behind it that takes the infrared radiation, not just it comes out the front, but takes the infrared from the back and bounces it back toward you, and hence helps to keep you warm. The same principle is used with the heat lamps you find at restaurants when you place your order, and it's still up there on the table with the heat lamp. Why is it still up there? I've been up there for 10 minutes, hello, and you can never get the server. But the infrared radiation actually helps in that score. The picture on the left is actually one I took with an infrared attachment to my phone, and this is in the parking lot at UCSB in the morning after everyone has just arrived. You can actually see that the hoods of the cars are glowing. That's the heat from the internal car. As I said, JWST is a mostly infrared telescope. The other thing you notice about it is it's a big telescope. It's the largest space telescope that's ever been built, certainly the largest one ever to be placed on orbit. Just to give you the sense of the scale, the mirror, which actually collects the light to make the images, the primary mirror is about 6.5 meters in diameter. It's not a single mirror, it's actually 18 individual mirrors that were folded up inside the spacecraft as it was launched out into orbit, and then had to very carefully unfold. And happily, all that worked. Put that into scale. Notice in this picture, we also see the primary mirror for the Hubble Space Telescope, which had been the previous record holder for largest space telescope, and that's only about a little bit more than 2 meters. This thing's much larger. The advantage to having really large telescopes like that, we'll see that in just a minute, just to show you that another sense of the scale is that it's not just the mirror sitting up there, it's sitting on this huge sun shield. Because it's the infrared telescope and because we saw things near room temperature actually emit infrared radiation, that means that if we didn't keep the telescope cool, basically it would be glowing in the infrared and it would be outshining the things that it's trying to look at. So it has a huge sun shield. It always faces toward the sun. The telescope is always faces on the side away from the sun. And that thing's super effective at keeping it nice and cold. And that thing's comparable in size to a doubles tennis court. So again, really huge deal. Because it's big, it turns out you can see dimmer objects. Think of what happens when you go into a dark room and your eyes open up. The iris of the eye opens up. It's increasing the light collecting area so you can see things that are otherwise dimmer. And this is a really big eye in that sense. Also, it turns out once you're above the Earth's atmosphere, which is where JWST operates, the larger the telescope is, that also gives you a sharper image. That's not the case for ground-based telescopes because the turbulence in the atmosphere puts a limit as to how sharp images can be. But once you've got stuff above the Earth's orbit, the bigger the telescope, the sharper the images can be. And I'll show you some really good examples of that going forward. Just to show you the difference between Hubble Space Telescope and JWST, this is a GIF that bounces back and forth between a Hubble image, which you're seeing right now, and a JWST image there that's circled. And if you have a big enough monitor, you can actually see within those circles, there are small red objects that would not have been visible at all in the Hubble Space Telescope image. Because those are things that the light we get from them is primarily in the infrared. See very little visible light. You also notice some of the colors of the other objects. Just about every object you see in there is not a star, but a galaxy of stars. For instance, the one toward the lower left, when you go between the Hubble image, where it's kind of red, and the JWST image where it looks much brighter, is because that galaxy is much brighter in the infrared than it is in the visible. Some of the other ones that give off more visible light than infrared, those actually look fainter in the JWST image. So it's clear this is complementary to the kind of data that you get from previous space telescopes. And it's not just that you can see objects you couldn't see before, there are aspects of the objects that you cannot see with previous telescopes as well. And we'll get onto that as we proceed through this. In order to stay cool and well away from any effects of the sun, JWST actually orbits at this point called L2, which is out beyond the moon's orbit, about 1.5 million kilometers from Earth. It actually sits there, so it's pretty much always on a line with the spacecraft, the Earth, and the sun. Again, with that sun shield always facing toward the sun, so that JWST is on the other side. That means if you want to look at a certain part of the sky, it means you can't do it any time of the year. You can only do it on the time of the year when the sun is basically not in the way of what you're trying to see. But that's really not much different than a Earth-based telescope, where if you want to see for instance, if you want to look at the constellation Sagittarius, that's a good thing to do in a northern summer, and it's a terrible thing to do in the northern winter because the sun's up at the same time Sagittarius is. So that's where it sits. So it's a big telescope and it's a long way away. So there's a lot of infrastructure with building it and keeping it in operation. Talking about infrastructure, the planning on this actually began back in 1989, a year before the Hubble Space Telescope was even launched. So even before Hubble was launched, they were already planning the successor to it. And it took a while to do it, but launched in 2021 and began operation the following July. So it's been up there a bit more than 2.5 years. And as a result, we got a bunch of really cool data from it. The question is, what have we discovered so far? The short answer is a bunch. But we only got about an hour here. So what I've done is I picked out 4 topics that seem particularly entertaining and accessible with I'm happy to say, no math involved. Well, there is one equation, but it's a pretty easy one. I want to talk about some of those during the time we have together. So the first thing I want to talk about, and this is really one of the key reasons why JWST was built the way it was to study galaxies in the early universe. And by early universe, I mean as close to the Big Bang as you can possibly get. Big Bang happened about 13.7 billion years ago. We will probably never know very much about what it looked like during the first 400,000 years after the Big Bang, because during that first 400,000 years, the universe was so dense and so opaque that even with the best telescope, you couldn't really see anything. But after about 400,000 years, the universe cooled to the point where it became transparent, and anything after that is fair game. So we'd like to see as far up against that 400,000 years after the Big Bang limit as we can possibly manage. So how far can we get, and what does it take to see that? Well, if we want to study the early universe, I mean, when we look at things that really happened a very long time ago, indeed in a galaxy very far, far away. And the key thing is that, remember that in astronomy, the farther away you look, the farther back in time we're looking. So to look at things very far away means looking very far back in time. So if we want to see what's happening very early universe, we have to look at very great distances. Here's a sort of more earthly example of that. Here's this wonderful panoramic picture of a city with the moon and some stars. And up at the upper left, you'll see the bright star Antares in the constellation Taurus. And the moon is about 400,000 kilometers away. And at the speed of light, it takes light from the moon 1.3 seconds to reach us. Incidentally, that's a long enough a time delay. That's why when you have spacecraft landing on the moon, like the recent Blue Ghost, a spacecraft that landed on the moon just a few days ago, the landing has to be done by the onboard computer. You can't control it from Earth, because if you see something going on, that means you're really seeing what happened 1.3 seconds ago with the T signal to reach you. You send your command, no, don't do that. And it gets there 1.3 seconds later. So 2.6 seconds have elapsed. And by that point, the spacecraft has already crashed. So that's why you need to do autonomous stuff, or else have the astronauts on board the spacecraft actually doing the landing. So again, when you're looking at the moon, you're not seeing the moon as it is now. You're seeing it as 1.3 seconds ago. For that matter, when you're looking at the screen right now, you're not seeing what's on the screen right now. You're seeing what was on the screen about a billionth of a second ago. That star Antares up at the upper left, that's 555 light years away, which means light would take 550 years to travel that distance, which means we're not seeing that star as it was today. We're seeing as it was 555 years ago. We'd say this is what the star looks like now in everyday parlance, but really you're looking further out in time. When you look at the Andromeda Galaxy, 2 million light years away, you're seeing as it was 2 million years ago, and so on. So if we want to look, as I say, really far back in time, that corresponds to looking at ever-increasing distances. And to see very far back in time, it turns out you need an infrared telescope. And the reason is that the universe is expanding. There's lots of misconception of what it means to say that the universe is expanding. This cartoon, which is actually from some of the stuff I'm doing with my colleague Wanele, actually points some of that out. People have the idea that if you look out in space, you'll see all the galaxies that seem to be moving away from us. And that might lead you to believe, like the cat in the left-hand cartoon, that, oh, you mean I'm the center of the universe? Well, cats usually believe the center of the universe, but in this case, they're completely wrong. What's really happening is, think of all the galaxies like spots painted on a rubber sheet. And you stretch the rubber sheet in all directions, which means that everything moves further away from each other. So in this example, the distances on the grid lines increase by 50%, which means all the objects are 50% further away from each other. And everyone seems to be moving away from everybody else. So in an expanding universe, there is no center. Everyone looks like everyone is going away from them. That's sort of the paranoid picture of the universe, that everyone is running away from us because they hate us. But what's really happening is everything is expanding. And so as a result, everything seems to be moving further away. By the way, that does not mean we are personally expanding or our Earth is personally expanding. Things that are held together by forces like the chemical force that hold our body together, the gravitational force that hold the Earth together, that makes them exempt from that overall expansion. But space itself is literally expanding, which means things in space expand along with it. And one of the things that's in space that expands is light. Envision light as a wave. So think of drawing a wave onto a rubber band. And if you stretch the rubber band, analogous to the expansion of the universe, that means the wavelength is going to expand as well. Well, that's exactly what happens to light as it's traveling through space. Light coming from a distant galaxy, which could take millions or billions of years to reach us, as it travels along, the space to which it's traveling expands. And that caused the wavelength to expand. And the further away we look in time, in space, the more time it's had to expand. And so correspondingly, the greater amount of red shift. We call it a red shift because in the visible spectrum, longer wavelengths go from blue to red. So you're shifting toward red wavelengths. Here's our one and only equation, the redshift, which you get the symbol Z, which is a natural choice because the word redshift has no Z's in it whatsoever. So it's a natural choice of symbol. It's the difference between the wavelength we measure from that object minus the wavelength that was originally emitted divided by the amount you started with. Basically, it's the fractional change in the wavelength that we receive compared to what it was when we were emitted. So here's some examples. So down at the bottom of the lower left, that's a spectrum that you'd get from a star. If you went out with a spectroscope and actually looked at the spectrum of our sun, it looked very much like this. It's a continuous spectrum. It's basically white light, but has dark lines in it, where certain wavelengths are absorbed. And what's absorbing? Is that our atmosphere? No, that's actually the atmosphere of the star itself. Our sun has an atmosphere. If you've been fortunate, for instance, to see the eclipse last year, you can actually see the solar atmosphere pretty clearly during the eclipse, and certain chemical substances in the atmosphere absorb certain wavelengths, and as a result, you get these dark lines in the spectrum. Well, if you've got a galaxy that's, say, at a redshift of 0.01, which means it's moving away from us, that corresponds to a 1% change in wavelength, you'll notice those dark lines have shifted a little bit to the right in our picture toward the red. The one above that, a more distant galaxy with a redshift of 0.15, that's a 15% increase in wavelength. Those wavelengths are shifted even further. You can see those lines shift. And a very distant one might have a wavelength shift of a redshift rather of 0.3, a 30% increase in wavelength. So if you can see those spectral lines, as they're called, in the spectrum of a distant galaxy and compare them to a reference here on Earth, you can actually tell what the redshift is. And from knowing the rate at which the universe is expanding, you can convert that to a distance. More properly, you can convert it to a look-back time. The problem with measuring distances in space is that, oh, that galaxy is a certain distance away from us. Well, it was a certain distance away from us when the light left, but it's moved since then. So it's probably easiest just to describe this in terms of look-back time. When we see a certain galaxy, how long did it take the light to reach us? And the greater the redshift, the further away it is, and the greater the look-back time. And we'll measure things in giga-years or billions of years. Put that in perspective, the age of the Earth is about 4.6 billion years. So for these numbers, for instance, a galaxy with a redshift of 0.01, a 1% redshift, that's about 0.13 gig years, or you're looking back about 130 million years. So that's a nearby galaxy. It's only 130 million light years away. And a more distant one out there, the look back time, 3.3 billion years. At that point, there was no life yet on Earth at all. Even with these fairly small ones, even as you can see, the redshifts are substantial, and that corresponds to pretty distant distances. Well, notice here, look at the wavelengths down at the bottom. We can see out to about 700 or 750 with the naked eye, but these things are being shifted up to wavelengths beyond that. In other words, you've been shifted into the infrared. So if we want to see these distant galaxies and measure their spectra, and hence measure how far away they are from their look-back time, we need to have an infrared telescope. And that's what JWST was primarily designed to do, was to detect these super distant galaxies with really long look-back time. How well has JWST done? Well, as of today, here's the current record keeper. Remember we said a distant galaxy might have a redshift of about 0.3. This one's 14.3. So the wavelengths have increased by on the order of 1,400%. It's been a huge shift. That corresponds to look-back time. As you can see, it's absolutely horrendous, about 13.52 billion years. Remember, the universe is only about 13.6 billion years old. So we're seeing this galaxy as it was just 285 million years after the Big Bang, which is pretty amazing that in only 285 million years, this galaxy has been able to form. And that just means not just that this big clump is formed, but stars are formed within it, because the light we see from that is due to the stars within that galaxy. It's a relatively small galaxy. It's only about 1,600 light years across compared to something like 87,000 for our galaxy. So the notion of reducing galaxies like this at these huge distances, but they're really small, the notion is that what we're seeing is something that's going to become the building block later in time of larger galaxies. It's thought that our own Milky Way galaxy was not formed from one big clump of gas, but rather by smaller galaxies that accumulated together. And this is essentially one of those building blocks. Using JWST, the astronomers are trying to find more and more of these really distant pieces to get a better sense of what these galaxies were like, how rapidly they formed. Again, only 285 million years to build a galaxy for something on that scale, actually fairly impressive. And some people have been surprised at how many of these really high redshift, really long look-back time, very early galaxies we're seeing. And so the folks who actually model the manner in which galaxies are formed in the first place are keeping fairly busy trying to keep up with all these observations. There you can see one reason why you really need an infrared telescope to see this. Part of the spectrum, the visible spectrum, has been shifted way over the infrared where you would never see it. And as you can see, this is a very small inset of a large photo. That's a really faint object, which means you need a gigantic light collector to do it. And that's why you needed that huge mirror on JWST. Another cool thing that JWST got involved in is actually looking at supermassive black holes and galaxies. So supermassive, always impressive, except when you go in for your checkup. And black holes also super impressive as well. This is an artist's impression of one. No one's actually ever seen one at this close range. I would not recommend getting too close to a black hole if you know what's good for you. So the question is, do we see these? How supermassive do you have to be these supermassive? And what kind of galaxies do you see them? Well, I know one fairly nearby galaxy where you can actually see one of these fairly well with telescopes. In fact, there's our galaxy. This is a wonderful view looking, actually, it's a panorama of the Milky Way. And for those of you who are going to Africa soon, definitely make sure when you're out on safari, go out and do a night drive, because you'll be there at a good time of year actually to see the Milky Way at night. And in the southern hemisphere, it's really high up in the sky. So yeah, definitely make sure you take a look at that. The thickest part, which is sort of over on the right near the horizon there, that's looking toward the constellation Sagittarius. And if you zoom in on that a little bit with an Earth-based telescope and watch for a long time, this is actually 20 years of observations made into a really pretty short GIF. And you see these stars, and look at the ones in the center, they seem to be orbiting around something. Can you see what they're orbiting around? The answer is no. There's something there. And to make an entire star go around an orbit that takes about 20 years means it must be something fairly substantial. And it's an unknown object, and given a very dramatic name. It's called Sagittarius A star. And through a variety of pieces of evidence, for instance, looking at how rapidly things go around, knowing what the mass of that star is, how far away, how fast it's moving, you can use some actually simple freshman physics to figure out what the mass of the object is that it's orbiting around. And you find that it's something about 4.3 times the mass of our sun, 4.3 solar masses, and it's really small. And the only thing we can imagine that's of that size, that mass, but so compact, is in fact a black hole. So this is a black hole with, as I say, about 4.3 million times the mass of our sun. This is a radio telescope image showing that you're not actually seeing the black hole itself. The light you're seeing in this thing that looks like a really fuzzy picture of a donut, that's actually light from stuff in the background that's being bent around the black hole by the intense gravity of the black hole. But the black hole itself is tiny. It fit easily within Mercury's orbit, which is really impressive for something with that huge amount of mass. You might think, oh my gosh, well, that must be most of the mass of our galaxy. Well, in fact, our galaxy is something in the order of 400 billion stars in it. So the fact this is only, quote unquote, 4.3 million means it's a tiny fraction of a percent of the total mass of our galaxy. But nonetheless, it's pretty impressive. And you don't just see it in infrared, and you don't just see it in radio waves, you can also see it with X-rays. So you've got this huge black hole. What happens to stuff when it falls into a black hole? Well, first of all, don't expect to get that stuff back because it's not coming out again. But as gas falls into the black hole, it gets compressed. And it gets compressed, it gets heated. It gets heated to such intense temperatures, millions of degrees, that it actually emits X-rays, that's light with wavelengths even shorter than ultraviolet. And this is a composite picture of both looking at the center of the galaxy, both infrared and also the blue is from another space telescope that's sensitive to X-rays. When I say this, that was an X-ray image, people think, oh, X-rays, that means you're taking an X-ray of the center of the galaxy. No. When we use X-rays in a medical setting, we need a complicated device to produce the X-rays, which are then sent through the human body. And they're particularly good for looking at bones because X-rays go through soft tissue, but they don't go through bone. And so it's easy to, that's how you can find whether you broke something, for instance. But as you can see from the picture on the left, it takes some fairly impressive hardware just to manufacture those X-rays. And there they can only do it for maybe a second or two before they have to shut it off because the energy consumption is so high. But in a supermassive black hole, as in this artist's impression of the lower right, as stuff actually goes into the black hole, and rather than falling in, it tends to spiral in along what's called an accretion disk. As it gets closer and closer to the center, it gets compressed more and more and emits these copious amounts of X-ray. So keep that in mind. Black holes, really massive, but also they tend to be strong X-ray emitters as well. So great, we got one at the center of our galaxies. Are we unique in that regard? Or do other galaxies have these as well? And the answer, it turns out, is almost everybody's got a supermassive black hole at the center of their galaxy. Here are 3 examples. NGC 3842, the names of these galaxies are so poetic, it's amazing. M87, NGC 4151, all these things have been found to have black holes that are centered. And there's 2 ways you can do that. One is looking for the X-rays, and the other one is for looking for, you can actually see things, even though you can't see individual stars, you can still see things about the motions of stars close into the center of that galaxy. And you can do the same kind of tricks you did for our galaxy to tell whether there's a black hole there. M87, the one in the middle, is kind of interesting. You can see there's like looks like a blue thread, almost like someone had a string attached to M87. That's actually material that was trying to fall into the black hole but missed. It got sped up tremendously as falling into the black hole, but it wasn't just the right angle to go in. So when that happens, it gets shot out perpendicular to that disk of material falling in and produces this huge jet of material. And that jet of M87, we can actually measure the speed of material and M80 stuff coming out, and it's a good fraction of the speed of light. So it's a black holes, on top of everything else, they're also natural particle accelerators, which is really quite amazing. But for even these, the ones like lower left, NGC 3842 with that 9.7 billion solar mass black hole, still only about 1/10 of 1% of the galaxy's total mass. And it's thought those things started as something smaller. Our notion is that black holes originally started as stars that die out and collapse into a black hole. A couple of those might coalesce and make a bigger black hole. We've actually seen this happening. You get a few more of those, and over time you could build up something really impressive. So the thought is these things started small and just got bigger as time went by. So what happens if we look at these really distant galaxies like JWST has seen? Well, the prediction is, well, if black holes started off small and then just grew with time, then very distant galaxies, which means you're seeing them in the very early universe, showing if they have black holes at all, they should be pretty small. And so what does JWST actually see when you go looking for those black holes? And the answer is, you see some small ones, but you see some huge ones as well. So this is actually a combination of some JWST image and one from Chandra, which is an orbiting X-ray telescope. The purple that you see here is actually the emission from Chandra. There's one particular galaxy in here whose redshift they've measured. It's over 10. So look back time takes it, you're seeing it as it was about 470 million years after the Big Bang. You can see from the inside, the upper left, it's got a huge amount of X-ray emission, which means it's got a big black hole in it. And that big black hole is actually bigger than the one in the center of our galaxy. It's about 40 million solar masses, which is at least 10% the mass of that galaxy. Remember we said for the ones in our nearby universe, those black holes, as big as they are, represented less than 1/10 of 1% of the galaxy's mass. So why is this thing so big, and how did that actually happen? The best explanation we have for the moment is that the black holes we see in galaxies like this were not formed from stars, but instead they may have formed by the process that had been proposed by theorists, that if you get some really massive clouds of gas and dust in the early universe, they could have just come together and formed a really massive seed, and basically formed a black hole all by themselves. That's probably not possible in the present day universe, but did happen, as far as we can tell, in the very early universe. So there's a lot more work to be done on that. I think it's really quite wonderful that we found something that didn't fit the models at all. Here's this supermassive black hole that's there much earlier than it should have been. The question, how did it get so big so fast? This may be the right model, but there's a lot more data being taken on these. And next time I give this talk, I may have a different answer for you. Here's where this comes from. So again, really cool, we're seeing all this stuff. And that's also a good example of how it doesn't just take infrared observations to make these things happen. You need things with other telescopes as well. The buzzword that's used among astronomers today is this. It's called multi-messenger astronomy. You don't just observe in one wavelength. You may look at the same object over a very broad range of wavelengths, and that could tell you things you couldn't get from any one telescope alone. I said we were going to go from the very farthest parts of the universe to our solar system. So now that we've gone to these dizzying distances back in time, or durations back in time, let's actually look close to home. Let's look at our own solar system. Let's look at one of the moons of Jupiter. Jupiter, pretty close. It's only about 5 times as far away from the sun as we are. And Jupiter's actually been pretty prominent in the evening sky of late as well. But I don't want to look at Jupiter itself. I want to look at its moon, Europa. Because it's 5 times further away from the sun than we are, that means it only gets about 1/5 squared, or 1/25th the amount of sunlight that we get, only about 4% the amount of solar energy, which is why on a sultry summer's day at the equator of Europa, daytime high is about -225 Fahrenheit. So bring your parka, and bring a parka for your parka and all that, and get used to drinking liquid nitrogen. Not a very pleasant place to be. But you notice that it's a weird looking moon. Doesn't look very much like our own Earth's moon at all. It has a very different texture to it. Let's look at that and see, where does that difference possibly come from? Interestingly, Europa is not too different in size from the moon. This shows the Earth, the moon, and Europa to scale. We know a big difference between the Earth and the moon is that while the Earth is geologically active, something that in California we knew all too well, because that's where all the earthquake activity comes from, the moon, by contrast, is pretty much geologically dead. And it's because the moon is small. Both the Earth and the moon, when they were young, were largely molten throughout their interiors. So there's a lot of heat, but over time they've cooled down. Now the Earth, because it's larger, has retained much more of that heat, but the moon hasn't. The analogy there is, think about taking a 20-pound Thanksgiving turkey out of the oven, or taking a meatball out of the oven. Well, an hour later, the turkey's still warm on the inside, whereas the meatball is cold, greasy, and disgusting, and ready to be served at the UCSB student cafeteria. Well, the moon, in that sense, is the meatball. It's had 4.5 billion years to cool down, and as a result, not much has happened there geologically ever since. They did leave seismometers. When the Apollo astronauts went to the moon, they left seismometers on the surface, and they do occasionally get seismic readings, but it's from meteoroids smashing into the surface. There's no endogenous, or very little endogenous, earthquake activity on the moon at all. And that's why, in this close-up, you can look at the moon, most of the features you see are actually craters. And because the moon, rather, has been geologically inactive for so long, when a crater happens, nothing happens to clean it up. There's no oceans to erode it away, certainly no atmosphere to erode it away. So once a crater happens, it's going to be there almost pristine for hundreds of millions or billions of years. Well, that's the moon in the upper picture. Here's Europa in the lower. And I think I see a crater. Now this is strange, because Europa, again, even smaller than the moon, you'd expect to be equally, if not even more, geologically inert than the moon is, but it looks, in fact, like the surface, if there should have been a comparable number of craters, in fact, maybe even more, because Jupiter has so much mass, you tend to attract meteoroids to its neighborhood, and yet I don't see any impact craters. The note, it's not that Europa has not been hit, it's that those craters have been erased. There's been geologic activity that have erased them. And the question is, how could that happen for something this small? And the reason I said it because Europa is not out there orbiting by itself. There are three of the inner moons of Jupiter, Io, Europa, and Ganymede, which are all named for lovers of Jupiter in mythology. And over the eons, their orbits have actually gotten into sync with each other. So for each orbit that Ganymede, the outer of the three, makes, Europa makes exactly two. And not just roughly two, but exactly two. They're totally synced up. And Io makes four. So whenever the colors in these change, it means there's a conjunction between the two, and one moon passes the other. So think what happens if you're Europa. Of course, Jupiter's gravity is keeping you in orbit, but when either Io passes you on the inside track, or you pass Ganymede on the outside track, you get a gravitational tug when that happens. And because these things are in this rhythmic pattern, these tugs are rhythmic. So as a result, what happens is there are these, as we call them, tidal forces that act on Europa that tend to stretch it and then relax it, stretch it, then relax it from the gravitational pull of those other moons. And it's much the same effect you'd have if you took a ball of putty and sort of rhythmically worked it in your hands. What would happen to that over time? You'd feel it getting warmer. And that's what's happening in Europa. Unlike the Earth, where the heat to generate geologic activity comes from inside, both the remnant heat from its formation and also the heat from the decay of radioactive materials. For Europa, that's actually caused by gravitational effects that are heating it up. And that's causing the geologic activity. But it's different geology than you get on Earth. As I said, Europa is really cold. It means that out there there's water, but water behaves like ice, and that ice behaves like rock. So what you're actually seeing, the geological activity you're seeing, is what we think of as rock, and the motions of molten rock as being geologic activity on Earth. On Europa, it's water and with liquid water and ice being moved around. And below the surface is thought to be a tremendous amount of water acting in the same fashion as the magma deep within the Earth's interior is acting. So it's water-based geology instead of rock-based geology. And just like on Earth, things will happen to move the surface around, form mountains, tear mountains down, and so on. It's the same thing happening on Europa. It's not been confirmed, but it's thought there are actually volcanoes on Europa, but they're ice volcanoes. And a lot of the weird features we see on the surface are actually due to stuff being moved around by this internal activity of the liquid water beneath and causing that erasure of features on the surface. In fact, it's estimated from measuring what the mass of Europa is and how the mass is distributed, which you can measure from passing spacecraft. It's thought that Europa actually has more water than all the oceans and ice caps on Earth put together. So really pretty fascinating place. And the question is then, okay, if there's water there, we know wherever there's water on Earth, we know we find living creatures. It may just be microscopic, but we find it. So the question is, could that be what's happening on Europa? Could there be life below the surface? On the surface itself, probably too cold. This is a close-up from the Galileo spacecraft of some of this weirdly jumbled terrain, which is really called chaotic terrain on the surface of Europa. But we know below the surface there's liquid water. So could there be life beneath the surface? Well, we know that if you want to have life, certainly life as we know it, that requires carbon. We are indeed a carbon-based life form. And exactly, live long and prosper and all that stuff. And so the question is there carbon in the ocean? Well, the ice cap, basically the crust on Europa is so thick, we have no way to really think about drilling down in there. But remember we saw this notion that because of geologic activity, stuff can come up to the surface. Just like we have volcanoes happening on Earth, maybe some of that material comes up on the surface. So the idea is that let's look for carbon compounds, in particular carbon dioxide, that might have shown up on Europa's surface. And exactly the kind of terrain I'm looking at here is just the sort that we want, because this sort of chaotic terrain is thought to be where stuff has been pushed upward and jumbled around. So maybe that's allowed some of the carbon dioxide to leave onto the surface. We do know about some of the chemical composition just in this picture. You know, some areas that look kind of yellowish or brownish, and they've looked at the spectrum light for that. That's sodium chloride, which means there is an ocean. The ocean beneath it is actually relatively salty. So the idea for looking for carbon dioxide is to use fluorescence. Now, we use fluorescence actually in fluorescent light tube. Fluorescence means that you hit something with light of a certain wavelength and it re-emits light of a longer wavelength. In ordinary fluorescent light tube, the mercury vapor inside the tube actually emits ultraviolet. If you take the coating off, that's a black light, and that black light emits ultraviolet, and the coating takes that ultraviolet light and emits it as visible light. Incidentally, if you go to a club, and you all look like you're the age where you go clubbing almost every night, if you wear a white shirt at a club, it really glows. And the reason is they actually put fluorescent material in ordinary detergent to make your clothing whiter than white, and you can really see that when you go to a club. I used to do a demonstration with the students where to show where the ultraviolet was in the spectrum, I just put up a freshly laundered handkerchief. And because the detergent there would actually, the ultraviolet would make your handkerchief glow at just the right wavelength. Well, carbon dioxide does the same thing. It absorbs visible light and can actually emit infrared at certain very distinct wavelengths. And of course, you all know what carbon dioxide is. That's just dry ice. It's this curious stuff that under conditions on Earth can be a gas or can be a solid, but cannot be a liquid. So basically, we're looking for dry ice on the surface of Europa, and we're going to do it using a target area like this one, looking at this chaos terrain. And that's where stuff has been shifted and rotated and moved around. But the reason that's interesting is that allows stuff, actually liquid, to leak up from deep below the Europa crust and leak out on the surface, and maybe let some of that carbon dioxide come out to the surface and freeze under the very low temperatures that you find there. So here's a picture of Europa from JWST. And you might say, well, that's kind of disappointing compared to the picture we just saw. And it is. Remember the picture I showed you before was one taken from the spacecraft, a couple 100,000 kilometers away. This is taken from near the Earth, a few tens of millions of kilometers, hundreds of millions of kilometers away. So that's pretty darn good when you look at it. And the one area we want to look at in particular, which corresponds to the picture I showed you earlier, is the one that's labeled right there. It's called Terra Regio. In the nomenclature from the International Astronomical Units, these broad regions of Titan are named for places that are important in Celtic mythology. And so Tara, which is actually, by the way, the same name that you'll run across for the O'Hara family in Gone with the Wind, was actually the main royal residence of the high kings of Celtic mythology. Well, I'm not sure whether there are any high kings on Europa, but if you look at Europa through the right filters, looking for infrared, here's what you see. Again, pretty low resolution images. The white is where you see actually the strongest fluorescence. And that corresponds to exactly that area called Terra Regio, exactly that area where we would have expected carbon dioxide to leak onto the surface. So we're actually seeing that carbon dioxide fluorescence on the surface. This is really good evidence that, in fact, there is carbon compound below the surface within the planet-wide ocean on Europa, because we see some of that stuff that's been able to leak to the surface and actually see its infrared fluorescence. So it would be impossible to do because this is pretty darn faint. So you need a huge infrared telescope to do it, and that's what JWST is all about. So it's nice to see something of design for looking at objects at the very extreme limits of the observable universe can also be used for stuff that's kind of happening in the local neighborhood. Can we learn more about Europa? And the answer is absolutely. In fact, I'll come back and give a talk in about 5 or 6 years because there's a spacecraft on its way to Europa right now. Europa Clipper was actually launched just a couple of years ago. Actually flew past Mars just a few days ago. And it's on this convoluted path where in order to make it out to Jupiter, it has to fly past Mars and flies past Earth to get a bit of a boost from our gravity. And we'll finally make it out to Jupiter in 2030. It won't actually go into orbit around Europa. Instead, it'll go into orbit around Jupiter. But its orbit will give us multiple close passes of Europa. They can actually observe at close range and actually have some instruments designed to actually look through the crust to get a little better sense of what's happening below the surface. The reason you don't want to put an orbit around Europa is Jupiter has a humongous magnetic field. When I say humongous, like don't even think about bringing your credit cards because they will immediately demagnetize. And in fact, the magnetic field is strong enough, it's probably not safe for you to go there either. The avionics on board a spacecraft like this, I was talking to a guy who actually builds cameras for another spacecraft called Juno that's right now in orbit around Jupiter. And that's sitting in a box with walls 3 or 4 inches thick just to screen it out from the magnetic field so the avionics doesn't get fried. So it'll do an orbit where it goes far away from Jupiter to get away from the magnetic field, then whips back in, time to give a close pass of Europa, minimize the exposure to the magnetic field, and come back out again. So hopefully I have some really cool information from that one. But again, another example of using multiple probes at multiple wavelengths and multiple kinds of spacecraft to study these objects out there in the universe. The last thing I want to talk about, kind of intermediate between our solar system and the super far away stuff I talked about earlier with very distant galaxies, is looking at regions where stars and planets are forming. This is another thing where infrared telescopes become super useful. Most people know the picture on the left of the so-called pillars of creation. It's part of the Eagle Nebula, which is 6,500 light years away. Sounds tremendously distant, but compared to what we were talking about before with stuff that were tens of billions of light years away, this really is the neighborhood. This is close enough, there's no redshift. This is all local stuff. This is a region where, as you can see on the left, where it looks like the dark pillars of dust and gas, and it's within such pillars that it's thought that stars actually form. And in the visible light Hubble image of the left, you can't really see what's happening through a lot of stuff because it looks like there's gas and dust obscuring things. But the infrared image on the right, which is from JWST, you can see much more stuff. What's really happened there is that you're actually seeing these so-called molecular clouds. They're called molecular clouds because, as the name suggests, they have molecules in them. Really diffuse gas clouds out in space are mostly hydrogen. Interesting, it's only about a century that we've known the universe is mostly hydrogen. Actually comes from the thesis of a woman in Britain, Cecilia Payne, whose thesis advisor didn't believe it, but she finally convinced her advisor to publish the paper. But she was the one who actually taught us, and now everyone accepts that that's very much the case. The universe is mostly hydrogen. 90% hydrogen, 10% helium, less than 1% that other unimportant stuff like carbon, nitrogen, oxygen, and stuff like that. But there are some places in the universe that are dense enough that atoms can actually find each other. When they find each other, it's beautiful because they form molecules. But those molecular clouds are the problem that visible light doesn't like to go through them very well. But infrared goes right through. And you can see that in the JWST image on the right. And how does that work? Well, here's an example. Here's a visible light photograph with a gentleman who's holding just an ordinary black plastic trash bag. The molecules that go into an ordinary black plastic trash bag are called polycyclic aromatic hydrocarbons, PAHs for short. And as you can see, they're very opaque to visible light. Interestingly, those are some of the same organic molecules we find in molecular clouds in interstellar space. Here's an infrared image of the same thing. And you'll notice that you can see right through that black plastic bag. The infrared, and this infrared radiation coming from the heat of his hands actually goes right through that bag, which is pretty cool. Interestingly, you'll notice that his glasses look dark. You can't see through them. That's why ordinary glass is actually opaque to infrared. And it turns out the Earth's atmosphere is largely opaque to infrared for the same reasons, which is another reason why you want to put infrared telescopes in space, because the atmosphere tends to blot out most of what you're trying to look for. Some wavelengths it works, most it doesn't. So again, visible light, really powerful for a lot of things, but to really see deep into these molecular clouds where stars are forming, you got to use infrared. Let's look at one local neighborhood that's even closer than the one I was just showing you. Let's look at the constellation Orion. Orion, one of the constellations most people can pick out. There's the bright star Betelgeuse at upper left, Rigel at lower right, the first and second brightest star in the constellation. The 3 stars that make the belt. The joke goes, Orion ordered a belt from Amazon and said, it was okay, I'll just rate it as 3 stars. And the 3 stars below it, which are supposed to be Orion's sword. But if you look at the middle star of that sword, it looks a little fuzzy. In fact, when you look at it with the naked eye, it actually looks fuzzy. And the reason it looks fuzzy is it's not a star at all. That fuzzy star in the middle is actually a nebula. It's a huge cloud of gas and dust, relatively close, only 1,340 light years away. And that is a region of active star formation. The reason you see it glowing is there recently formed stars in there. You can see some really bright blue stars in there. And those blue stars, in addition to giving out visible light, they give out a huge amount of ultraviolet. Well, think back to that fluorescent light fixture I was telling you about. The coating on a fluorescent light fixture absorbs ultraviolet light and re-radiates visible light. The gas around those stars is acting like a fluorescent light fixture. It's absorbing the ultraviolet light from those stars and re-emitting it as visible light. The biggest darn fluorescent light fixture you ever saw, and there it is, and it's been running continuously for millions of years, and continues to do so because there's no stars forming in there. So we'd like to know more about what's going on in there. And in fact, Hubble Space Telescope was very useful for that. Hubble, in addition to seeing in the visible, could see a little bit in the infrared and deliver these pictures. These pictures are now 30 years old. So these are what are called protostars. They haven't quite completely settled down to what a star is, creating energy by nuclear reactions at its center, but we also see these sort of black things around them. And those are disks around the stars. It's thought that from those disks, which naturally tend to orbit around the star and sort of flatten out because of their rotation, that from within those disks, planets form. And because you end up with a disk of material, that kind of stuff forms in there, that's why we ended up with a solar system where all the planets go around in the same direction and they all orbit in almost the same plane. So this, if you will, is a view of what our solar system might have looked like some 4.6 billion years ago. Well, that's old news. That's 30 years ago. The question is, what more can we see from JWST? So we're going to zoom in at the region in the box there, and it turns out from analyzing the recent stars in there and what we know about stellar evolution, those things are only about 300,000 years old. I think that seems pretty impressive on the earthly standard, but that's compared to 4.6 billion years for our sun. To put that in perspective, the ratio of the ages of stars in that region to the age of our sun is almost exactly the same as the ratio between a 3-week-old baby and somebody in their 60s. You'd think that 3-week-old baby, that one's pretty fresh, and the same thing is true for the stars we see in that inner region of the Orion Nebula. So what do we see? Well, here's a couple images, actually from JWST of that inner region. They're not quite the same. The one at the top was made with the shorter wavelengths. That's the one that are closer to the visible part of the spectrum. The ones at the bottom is in the longer part of the wavelength, though, out to 28 microns. And there you notice you can see a lot more stuff than you could have in the upper image. You're able to see through even more obscuration. And you can also see different features as well. It's interesting to note that the stars in the upper picture, there's the 3 really bright stars that you see at lower right. Interesting, you notice they have, looks like 6 points coming out from them. And that's actually because of the hexagonal shape of the mirrors and JWST. Those same 3 stars in the lower picture don't look anywhere near as bright. That's because of those longer wavelengths. Those are stars that are giving off most of their light in the visible part of the spectrum. When you go to the infrared, they're relatively faint by comparison. I don't want to get into all the details because there's so much stuff happening in there. What I would do is look at some super close-ups from within that region. And these are some more recent images of those protoplanetary disks in the Orion Nebula. These are ones we picked out because we see them almost edge on. So you look at those guys, and the reason they look edge on, even though the material in the disk is pretty thin, if you look through a few hundred astronomical units of that, and an astronomical unit is the distance from Earth to Sun, it begins to look opaque. It's kind of like if you took a cubic meter of smog, it wouldn't look that bad, but if you look through a few miles of it, all of a sudden you can't see very far. Same idea. And so these are all solar systems under construction. To give you a sense of the scale, the dot over at the left shows the size of our solar system to scale. These things are bigger than our solar system. A lot of the stuff in there will either dissipate away or perhaps fall into the sun, and the solar system remains to be relatively small, but still it's neat to see. You can see the solar system process of formation taking place in real time. But here's some other stuff that we didn't expect to see. These are planets, because we can tell from how faint they are that they're not bright enough to even be a protostar, and certainly not bright enough to be suns. They're free-floating planets without a star. And just you can see what I'm talking about. I circled them in this picture. And what's weird is we don't see them in isolation. We see them in pairs. And you think about it, if you're a planet all by yourself, you want company. There's no question about it. And they've got it. And these things are big. The numbers in there, N, 3M, MJUP, that means the one on the northern side, and north is kind of to the left in these pictures, has 3 times the mass of Jupiter. The other one is 7 times the mass of Jupiter. And they see these in all different masses, even down to ones that are only about half the mass of Jupiter. So the question is, how did these form? Do they form the same way as stars do? Were these part of a solar system and they escaped? Probably not, because it's so early on, there wouldn't have been time for that to happen. And why do they form in pairs? And why do they form at this scale? And in fact, it turns out they see even more of these with smaller mass than they do with the masses we see here. You notice they're called jumbos, and jumbo, of course, is a wonderful acronym. It's Jupiter Mass Binary Objects. If you define something new in astronomy, you have to come up with a good acronym. At the moment, we don't have a real good sense of where these come from. Now, again, these are Jupiter-like planets, but you could certainly imagine having a moon like Europa orbiting a Jupiter-like planet like this, having another Jupiter-like planet in the sky, but no star. So imagine what that would be like. That would be cold, for one thing. The experience of that is something that I think would keep science fiction writers very busy as well. The next question I'd ask is, wait a minute, these are planets. When we go out at night and see a planet, if you see Venus off in the west or Jupiter overhead and so on, you're not seeing the light emitted by those planets. You're seeing light reflected from a star, in this case, our sun. So how can you see these at all? That's the question. How can JWST see planets that aren't illuminated by a star at all? And the answer is because it's an infrared telescope. And it turns out Jupiter-like planets actually emit infrared radiation all by themselves. This on the left is a JWST image of Jupiter. You'll notice there's that one bright spot just below the equator. In visible light, that's a dark spot. But in infrared, it's actually bright, which means that's hot because you're seeing deeper down into the Jovian atmosphere at that point. You're seeing deeper down. Just like in the Earth's atmosphere, it gets colder as you go up. Same in Jupiter, it gets warmer as you go down. Jupiter has the interesting property because it's mostly gas, it's slowly contracting. And as it contracts, it emits heat. And that heat actually emits infrared. And as a result, Jupiter actually emits more radiation than it receives from the sun. So it's that radiation that JWST sees when we see these free-floating jumbos, these free-floating Jupiter-sized planets out there for some reason that are in binary systems, and it's the infrared light that they're emitting that we're able to see. No one expected to see those things, but there they are. What other things can we talk about with JWST? Well, I've already gone for an hour, so I think I'm going to stop right here. And I will suggest if you want to keep up to date with all the cool stuff that's going on with JWST, there's several websites out there. The best one I've seen is the one run by European Space Agency, just esaweb.org. That'll keep you up to date with everything that's going on. It continues to be an amazing device. Took more than a decade from when it was supposed to get up there to when it finally got up there, but it was most definitely worth the wait. And at this point, I will stop and open things up to questions.
Wow, incredible. Do you regret having retired? Do you wish you were there in the classroom letting people know about all this stuff?
Oh, actually, because I'm still writing textbooks. I'm actually working right now on the 16th edition of my university physics textbook. So I'm getting to write about all this stuff right now. And actually, happily, because the books are used with such a wide audience, I'm getting to tell a lot more students than I would just in the classroom.
Oh, okay, that's great.
That question I was asked about being able to see in the infrared, I have heard the story of someone who got one of the first intraocular lenses as a surgery to deal with cataracts. And the guy was an amateur astronomer, and that early version of the intraocular lenses was actually slightly more transparent in the ultraviolet than your natural lenses. So he found he could see stars he hadn't seen before, because he's seeing stars that were relatively bright in the ultraviolet, but not in the visible. There are fish actually that see in the infrared. In fact, there are some marine organisms there are some fish that actually have infrared lamps on their heads in the deep ocean. And they use infrared because it travels. Yeah, and the infrared actually travels further than visible light would. And so it's literally able to see where it's going and to look for prey by using that infrared emission.
I'm wondering between the JWST and the orbiting telescopes and those that we have on Earth and the people who are responsible for both, are they cooperative with each other? Are they jealous of each other? I mean, what can you talk about the relationship of the people that
staff all these telescopes? Exactly. Everyone's super excited to work with each other. So for instance, I mentioned the idea of multi-messenger astronomy. A subset of that is what's called time domain astronomy. For instance, the things we've been looking at, if you went back and looked at the objects I looked at in my talk, if you came back a year later, they'd look pretty much the same. But there's some events that are really short-lived. like supernovae, for instance. When one of those happens, there's actually a system where it sends a message out to everybody, hey, this thing just happened, everybody look at it right now. If there's a space telescope that'd be appropriate to look at that thing, they'll slew it over to look at that thing right now. So it's actually super cooperative and keeps people really busy. One friend actually there in town at UCSB who was involved with a new type of exploding star that they saw, and he was actually on an airplane when this thing went off. So he was busy using the onboard Wi-Fi, telling everybody, do this. Okay, you guys go look at this. You guys look at this, and so on. So it's super cooperative. As a result, some of the papers that are published will have huge numbers of names on them from universities and research institutes across the planet, just because there is so much interaction on this stuff.
Yes, I was wondering, when the sun expands, will it take out Mars? And
Oh, that's a
Elon
good
Musk
question.
with
That is an interesting question. It is true that as the sun ages, it actually expands. And in fact, the sun is a couple percent larger now than it was when it was first formed. The reason that happens is as a star ages, the nuclear reaction in the center actually go a little faster. That produces more energy and actually pumps up the star. That's been a fairly slow process for the last 4.5 billion years. It'll accelerate as time goes by. In another couple of billion years, as a part of that expansion, the luminosity of the sun goes up as well. In another couple of billion years, the sun will be luminous enough that it'll melt away or evaporate all the oceans in the atmosphere. So hopefully we'll find someplace else to go by then. But it will eventually expand. I've seen different estimates that it's probably going to go out to the orbit of Mars, yeah, which is impressive considering how small it is now. And as it does that, it becomes very diffuse, but it's still super luminous, and the Earth will certainly be completely enveloped with that and swallowed up by the sun. But again, not going to happen for billions of years, so that at least is not going to affect your 401k.
Thank you.
That's good to know. And I did make a note, Roger, that you volunteered to come back in 2030 to talk about the Europa Clipper. So I'll put you down on the agenda for that in 2030.
Sounds good.
And really want to thank you. And for people who don't remember, Roger's talked to us at least twice before. September 2018, what Newton never knew about gravity. That was back pre-pandemic when we were live events. And then back in May 2022, Seeing into the Cold, when JWST was first launched. And that talk has been recorded, edited, and it's up on our YouTube channel if you want to go back and take a look at that. But with that, Roger, thank you so much for coming back and sharing all of this exciting stuff with us. I learned a lot and really appreciate you taking the time to share it with us.
You're welcome.